My topic for today is the holonomy group spin 7. So I have a section 5.6 on this. Sorry. Hi. The printed timetable is wrong, so we've adopted our own timetable. And well, if Jürgen wants to come along and say a few words, yes. the right kind of time would be 11:45.
11:45.
Yeah. Okay. So anyway, so this is the second of the exceptional holonomy groups. So spin 7 is a compact Lie group. So in general, the spin group SON is a double cover of spin N is a double cover of SON in any N. So spin 7 is the double cover of SON. And this is something which works in any dimension, and it has a representation the spin representation of spin 7, which in 7 dimensions happens to be a representation on r to the 8, and therefore this defines an inclusion from spin 7 into SO8. Okay, so and you kind of do this trick in any dimension, but spin 7 is the case in which it happens to be a holonomy group. I suppose actually spin 3 is SU2, which is also a holonomy group. Now, in fact, so in 8 dimensions, there are rather more choices of kind of holonomy subgroups of spin 7 than in the other cases. So in fact, we have the following diagram of inclusions of holonomy groups. So let's start with SO8, and then the space it acts on is, so that this round arrow is it means acts on. So SO8 acts on r to the 8. Sitting inside this is spin 7, also acting on r to the 8. I'm going to have a column here and a column there. So let's say on the left we've got a G2 acting on r to the 7 cross r, where the action of G2 on the r factor is trivial. And okay, so that G2 is contained in spin 7 as a subgroup. Going down one level, SU4 acts on C to the 4, which you can identify with r to the 8. And in here we can put SU3, which acts on a C3 direct sum R2, let's make that a direct sum too, where the action on the R2 is trivial. And this SU3 is included as a subgroup in both G2 and in the SU4. And go down another level, SP2 is a subgroup of SU4. We can think about that is acting on h squared, the two copies of h, the kind of quaternionic vector space h squared, which is also identified with r to the 8, or if you like with c to the 4. Swap the walls around. And finally, I'm going to put, well, SU2 cross SU2, or if you prefer, SP1 cross SP1, sitting inside SP2. This acts on H direct sum H, which is r to the 8. And here we can take just SU2 cross root 1, acting on, well, H or C2, direct sum an r to the 4, where the action here is trivial, and that can be included there. Okay, so there's a whole kind of tree of interesting holonomy groups there. Okay, so one consequence of this is that, well, if we produce a Riemannian manifold X of dimension 8 and G with the holonomy group of G contained in spin 7, we have to check that well, if you're aiming to produce a manifold with holonomy exactly equal to spin 7, we have to check that hol of G is actually equal to spin 7 and not SU4 or G2 or whatever else it might be. So in particular, well, so the left-hand side can only occur if the fundamental group is infinite in the compact case. But the right-hand side, these four things here, they can occur with simply connected 8 manifolds, so we're going to need some other test to distinguish between spin 7, SU4, SP2 and SU2 cross SU2. Okay. So let's take r to the 8 to have coordinates x1 up to x8, and again as a shorthand, let's write dx I j k l is dx I wedge dx j wedge dx k wedge dx l. And so as to the G2 case, the spin 7 preserves an interesting form on r to the 8, which is a 4 form. So let's define a 4 form, which we'll call big omega 0 on r to the 8 by so it's going to be a rather long formula. Omega 0 is so there's 14 of these terms, I think, dx 1, 2, 3, 4 plus dx 1, 2, 5, 6 plus dx 1, 2, 7, 8 plus dx 1, 3, 5, 7 minus dx 1, 3, 6, 8 minus dx 1, 4, 5, 8 minus dx 1, 4, 6, 7 minus dx 2, 3, 5, 8 minus dx 2, 3, 6, 7 minus dx 2, 4, 5, 7. plus dx 2, 4, 6, 8 plus dx 3, 4, 5, 6 plus dx 3, 4, 7, 8 plus dx 5, 6, 7, 8. Okay, so there's 14 terms here. This is actually Hodge dual to itself, so they come in pairs. For example, star of dx 1, 2, 3, 4 is dx 5, 6, 7, 8, and so on. Now the G2-3 form and the G2-4 form each had 7 terms. You can think about this as being built from the G2-3 form and the G2-4 form as something like omega is kind of dx 1 wedge phi 0 plus star phi 0 or something like that, if you chose the appropriate thing. So if you chose the appropriate numbering of the 2 up to 8 coordinates. Okay, so then the stabilizer group of this form big omega 0 in GL 8, R, which acts on the 4 forms on R to the 8, is this group spin 7. And okay, so this 4 form is a special 4 form, as we'll see. It's not generic, and most 4 forms would have rather smaller stabilizer groups than that. It's kind of a 4 form which is most symmetric, really, apart from something like 0. Yeah. Okay. So, well, hence, do I mean a 4 form that's least symmetric? Anyway, hence, by the relation between holonomy groups and constant tensors, if you have that x to the 8 and g is a Riemannian manifold with the holonomy group of G is equal to spin 7, or actually contained in spin 7 is enough, if you have a particular inclusion, as it were, then there is a natural 4 form big omega on X with nabla big omega is 0, where nabla is a Lev-achieved connection of G. So such that well, big omega and G are modelled on, or kind of locally isomorphic to, well, big omega 0 and your standard metric G0, which is dx1 squared plus up to dx8 squared at each point. Okay, so in the 7-dimensional case, what we had one 3 form phi, and then we took its Hodge dual to get another 4 form star phi. In this case, we have star of omega 0 is equal to omega 0 with our standard orientation, so it's self-dual, where star is the Hodge star. So you can't make another spin 7 invariant form from that. And Okay, another important fact is that metrics G with the holonomy group of G are contained in spin 7 are Ricci flat. That just comes from the fact that the holonomy group constrains the curvature tensor, and if you just look at the vector space of all possible curvature tensors satisfying first Bianchi and the first two indices lying in the Lie algebra spin 7, all those curvature tensors have no Ricci component. Okay, so as for the G2 case, I'm going to define a notion of spin 7 structure, which is actually an abusive notation. Let's make a definition. Well, let X be an 8 manifold. And then a spin 7 structure on X is a pair big omega G of a 4-form big omega and a Riemannian metric G on X such that, well, at every point little x in big X, there exist isomorphisms from the tangent space t little x to big X with a standard vector space R to the 8, which identify the 4-form omega at X and the metric G at X on Tx at big X with the standard versions omega 0 and G0, where G0 is defined wherever it was, the standard Euclidean metric on R to the 8. Okay, so that's an abusive notation because I've already told you what is usually meant by G spin 7 structure, which is this notion of G structure, a principal subbundle of the frame bundle of your manifold X with structure group spin 7. But in fact it's equivalent. So so this is equivalent to the usual notion of spin 7 structure as a principal spin 7 subbundle of the frame bundle. So equivalent in the sense that there's a one-to-one correspondence between spin 7 structures in that sense and spin 7 structures in this sense. Also, you kind of don't need to include G in this because the 4-form omega G depends only on big omega. So if you've got omega, you can reconstruct G, though not in a terribly obvious way. But it's just convenient to have the pair there, just for notational reasons, really. Okay, so let's have a proposition which is the analogue of the first result I gave you about G2 structures. If we say let big omega and G be a spin 7 structure on big X. So then the following are equivalent. So firstly, d of omega is 0. Secondly, nabla of omega is 0, where nabla is the Levi-Civita connection of G. And thirdly, the holonomy group of G is contained in spin 7. And that's not quite enough because you'll need also to say that big omega is the induced 4 form. In the sense that if you're given an inclusion of the holonomy group of G into spin 7, you can reconstruct a 4 form from it. Okay, so this may look initially a bit confusing because you'd think that the second equation is strictly stronger than the first one, but we'll get to why that can be true. Okay, so if all of these hold, then we call brackets big omega G a torsion-free spin 7 structure. So this agrees with the notion of torsion-free G structures I explained when we were talking about G structures. So you can think about d omega as being the torsion of the spin 7 structure. And we call also the triple X, comma, big omega, comma, G a spin 7 manifold. So for me, a spin 7 manifold is an 8 manifold with a torsion-free spin 7 structure. So some people would use spin 7 manifold without the torsion-free condition. Okay. Well, so let's explain why it can be that parts 1 and part 2 can be equivalent. So we'll note that, and here, in contrast to the G2 case, big omega 0 is not a generic 4 form on R to the 8. Okay, so for in the G2 case, the G2 3 form phi is generic in the sense that any nearby 3 form is also a G2 3 form for a different G2 structure. So the G2 3 form wasn't really special, but the spin 7 4 form is. So we can do a kind of back of the envelope calculation just in dimensions. So the orbit, the GL 8R orbit of omega 0 is GL 8, R divided by spin 7. Well, that's just true because we know the stabilizer group of omega 0 in GL 8R is spin 7. So this sits inside the 4 forms on R to the 8 star. So this is the orbit, just for general reasons, this is an embedded submanifold. fact a closed embedded submanifold. So let's look at what the dimensions are. Well, GL8R has dimension 64. Spin 7 has dimension 21. So the quotient GL8R divided by spin 7 has dimension 64 minus 21, which is 43. And the dimension of the four forms on R to the 8 are the binomial coefficient 8 choose 4, which is 8765 over 4321, which is 70. So this dimension is bigger than that dimension, and the so we see that spin 7 forms big omega have codimension uh, 70 minus 43, which is 27, in all four forms. Okay, so if you've got a spin 7 form omega, the condition for a form omega to be part of a spin 7 structure is a pointwise condition on omega that it should lie in a submanifold of all four forms of codimension 27. Okay, so thus in part 1 of the proposition, where it's gone, there, we should not regard d of big omega equals 0 as a linear equation since, well, it's a first order linear equation, but omega also satisfies a 0th order nonlinear equation. So since big omega is required to lie in a nonlinear submanifold, of the four forms lambda 4 t star of x, and so this is why d of big omega equals 0 can imply nabla of big omega equals 0. Okay. Right. So if we're trying to construct spin 7 manifolds or to study them, then we usually end up thinking about this equation d of big omega equals 0 for omega of the special form of being a spin 7 form, because that's this is a nicer equation to study than that one, because this has got many more components, but most of them are unnecessary. Okay, well, a spin 7 manifold x and big omega and g, by definition this is torsion free, so d omega is 0. This has a topological invariant the de Rham cohomology class of big omega in H4 de Rham of x, which you can think of as similar to the Kähler class of a Kähler manifold. So that might be natural. If you're trying to describe some spin 7 manifold, then maybe one of the first things you'd do is find out what that 4 cohomology class is. Okay, let's have a section 5.7 on compact spin 7 manifolds. So initially just on the kind of general properties of them. So let's have a theorem. So let's suppose that X and big omega, comma G is a compact spin 7 manifold. So this theorem is aiming to give us conditions under which the Coulombic group of G is equal to spin 7 rather than is equal to one of the quite a few other possibilities which we had in our diagram of Coulombic groups a few minutes ago. So firstly, if the Coulombic group of G is equal to spin 7, then X is simply connected. Okay, so that didn't happen for G2 manifolds or Calabi-Yau threefolds, for example. Those are allowed to have finite fundamental groups, but for spin 7 manifolds, also for even dimensional Calabi-Yau manifolds, they're forced to be simply connected. And the reason for that is that there's a characteristic class called the A roof genus, we'll talk about it shortly, which is forced to have a particular value, in this case the value 1, now for a manifold with Coulombic spin 7. And if you were to take a finite cover of your manifold with Coulombic spin 7, then the finite cover would also have Coulombic spin 7, so it would have to have the same characteristic class. However, if you take a finite cover, then characteristic classes get multiplied by the degree of the cover. So using that argument, you can show that if you have finite fundamental group for a Coulombic group such as spin 7 or SU2M, then the fundamental group is forced to be 1 rather than just finite. And so general facts about Ricci flat things will tell you that the Coulombic group of a spin 7 manifold has to be Coulombic spin 7 manifold has to be finite. Okay. So secondly, well, there is a topological invariant of X called the A hat genus, or if you're American it might be called the A roof genus, written A hat of X. It lies in the integers, and it's a characteristic class So characteristic classes are, well, they're some kind of cohomology valued invariants. In this case, it's taking values in the north cohomology, well, okay, which is the integers. So it's basically a, and it is the index of the positive Dirac operator. Okay, so this is good, something which is good for any compact oriented spin manifold. This topological invariant A hat of X is defined, it's an integer. Now, well, at least as X has structure group spin 7, it satisfies an equation in terms of the Betti numbers. So 24 a hat of x is equal to, well, minus 1 plus b1 minus b2 plus b3 plus b4 plus minus 2b4 minus. So these are the Betti numbers of x. I've assumed x is connected, so the 1 is b0. So the Betti numbers of x, this is a self-dual b4 plus, the dimension of the self-dual part of de Rham group b4. That's the anti-self-dual part of de Rham group b4. Okay, so this equation is only good for spin 7 manifolds, or manifolds whose structure group is reduced to spin 7. And so the A-roof genus exists for general 8 manifolds, actually for general probably 4n manifolds or something, but you can only write it in terms of numbers in this special case. But the good thing about that is that it enables you to compute the A-roof genus if you know the Betti numbers of your manifold, which are usually rather easier to find than the A-roof genus is. And then the third part says C, if X is simply connected, and this thing is a spin 7 manifold, so it has a torsion-free spin 7 structure, then A hat of X is either 1 or 2 or 3 or 4, and it determines the holonomy group of G, determines hol of G by, firstly, hol of G is spin 7 if and only if A hat of X is 1, and the holonomy group of G is SU4 if and only if A hat of X is 2, and the holonomy group of G is SP2 if and only if A hat of X is 3, and finally the holonomy group of G is SU2 times SU2 if and only if A hat of X is 4. So these are the 4 holonomy groups which occurred in the right-hand column of my group of my diagram of holonomy subgroups of spin 7, and you can distinguish all of them using this A-roof genus. Okay, so are you all happy about what the theorem actually says? Yeah. Okay, so so basically this enables us to test for when the holonomy group of G is spin 7 in terms of the topology of our 8-manifold X. So if we're trying to construct some compact 8-manifold with holonomy spin 7, then once we've constructed a torsion-free spin 7 structure on it, we just have to make sure that the that X is simply connected and its A-roof genus is 1, where we can compute the A-roof genus from the Betti numbers using that equation. Okay. So next let's talk about the deformation theory of spin 7 manifolds. So let's have a theorem. If we let big X be a compact and oriented 8-manifold, so I want the orientation because the sign of the A-roof genus depends upon the orientation. And as for the G2 case, I want to form a moduli space of torsion-free spin 7 structures on it. So let's write curly M is moduli space, which is going to be the set of torsion-free spin 7 structures big omega G on X. Well, I suppose I want, if I'm fixing the orientation, I want oriented, so I want them to be compatible with the given orientation, and then divide by diff 0 of X, which is the group of diffeomorphisms of X isotopic to the identity. So, well, the conclusion is going to be that M is a smooth manifold. If you divided by diffeomorphisms not isotopic to the identity, if you divided by all diffeomorphisms, then M might become singular. It might become something like an orbifold. So the conclusion is that then the M is a smooth manifold of dimension dim M. Well, in the general case, it's A roof of X plus B1 of X plus B4 minus of X. But actually, this is 1 plus B4 minus of X for holonomies of G equal to spin 7. Because if, in the case of holonomy spin 7, then A roof of X is 1 and B1 of X is 0. So it's a smooth manifold of that dimension, and also the projection from M into H4 diram of X R, taking the diffeomorphism equivalence class of omega G mapped to the diram cohomology of omega. This map is an immersion of manifolds. So roughly speaking, M embeds as a submanifold of H4, although you don't know whether it might kind of cross itself at distant points. Okay, so therefore metrics with salon B spin 7 come in positive dimensional moduli spaces. Bother, I've gone too slowly. If you don't mind, I'd like to overrun by a few minutes so I actually get to the punchline of my talk. Okay, so the same thing happens as before. Because spin 7 manifolds come in positive dimensional moduli spaces, there is the possibility of a moduli space of metrics in some sense having a boundary. And then at the boundary, the spin 7 structures decay into something simpler, into several pieces with reduced autonomy smaller than spin 7. Therefore, you can try and construct compact 8 manifolds with autonomy spin 7 by first constructing the pieces into which it falls and then gluing them together. So finally, we'll have a section 5.8 on constructing examples of compact 8 manifolds with holonomy spin 7. So, well, basically by me in 1995, there's a construction by resolving singularities of basically orbifolds of the form t to the 8 mod gamma and then kind of flat spin 7 structures. So your typical gamma might be, for example, z2 to the 4th would be the simplest examples. And okay, it's very similar to the G2 case, but then the details are kind of harder in almost every respect. So, well, finding examples is harder, and you need more complicated. You need to resolve more complicated singularities. So one reason is that so in the spin 7 case, in the G2 case, you could arrange to have your singularities of the form T3 cross a singularity and just separate them out. If you tried to do that in the spin 7 case, you would find that you'd produce something with a roof genus to 0, which, well, because you can show that using properties of characteristic classes. So it's actually necessary to have an orbifold here which has some kind of special points, and at those special points different orbifold strata have to crash together. So you need to work harder on what kind of singularities we can resolve, and also the somehow the deformation to torsion free, in some sense it kind of only just works. So, and if you do a naive calculation on how big the torsion is and how then you find that somehow you're at the cusp of where the method works, and so you have to work harder. You have to do a kind of first correction to the thing before you can apply some kind of simple method or simple-ish method. And also the business of working with these 4 forms which are not generic makes your life more complicated. But anyway, so in the end you just kind of push the program through, and you can get, many, I don't know how many, compact 8 manifolds with holonomy spin 7 with around about 200 sets of Betti numbers in my book, but actually you can distinguish different 8 manifolds with the same sets of Betti numbers by properties of the cut product on the cohomology, and therefore these represent probably a lot more than 200 distinct 8 manifolds. There's also there's a second construction where you start not with an 8 torus, but you start with you start with a Calabi-Yau 4 orbifold with singularities of a certain type. You divide it by an anti-holomorphic involution, and then you have to resolve this. So this still has singularities, and you have to repair the singularities of that. And this is, in principle, easier than that in some ways, because you can arrange to have a rather simpler singular set in that case, which is just some finite collection of points. Okay, so I'm sorry for having run over, and thank you also for listening.